Gases. After the last unit on stoichiometry, you'll see there's far less calculations here and a little more theory. Here's what we're going to cover. And speaking of theory, we're going to start with the kinetic molecular theory, which underpins everything in this chapter. Then we'll talk about different properties of gases, how we measure them, the gas laws, the ideal gas law, and then at the very end we'll show a few cases how reality differs from the ideal gas law. We'll talk about density and partial pressures. And here's a little disclaimer here. Not sure we have any in this unit, but that will apply to future units too. The kinetic molecular theory. This theory was developed by Ludwig Boltzmann in the late 1800s. It's based on the idea that matter is made up of atoms and molecules that are way too small to be seen. These ideas had actually been rejected by most scientists until the early 1900s, so Boltzmann was a bit ahead of his time there. The theory connects the microscopic world, actually submicroscopic, right? You can't see any of those guys with a regular microscope, of atoms and molecules with the macroscopic world, that's what you and I see, and it helps us greatly understand the behavior of gases. There are some key assumptions we make to understand the behavior of gases. Another name for assumption is postulate. Gas atoms or molecules are in constant motion, and therefore they have kinetic energy. Hopefully you remember from physics that's 1/2 mv squared. The faster the speed, the higher the kinetic energy. The collisions of these gas particles with the walls of a container that keeps them in are the cause of the pressure exerted by the gas. Think about blowing up a balloon. What you're doing there is putting energy into the system. The gas particles move around a lot quicker. They exert pressure on the balloon and it expands. Gas particles can be either atoms or molecules. Second postulate. The average kinetic energy of particles in a sample of gas is proportional to the Kelvin temperature. And we'll talk about that shortly. You're probably familiar with Celsius or centigrade, and then Fahrenheit. Kelvin's another one, and that's actually the standard that we use in physics and other sciences. The higher the temperature, the higher the average kinetic energy of the particles. So right here, this represents a low temperature gas. The vectors here show that the particles are not moving very fast, so they have a lower average kinetic energy. This is a high temperature. You have a higher average kinetic energy. Now actually, not everybody's moving at the same speed. For example, I could have one guy just moving very slow and another particle moving very fast, but on average, this will have a higher kinetic energy. I alluded to this last slide. Not all of these particles are moving at the same speed, so we're talking about an average kinetic energy. It's proportional to the Kelvin temperature. We're just continuing this from the previous slide. We have a graph here. We have number of molecules on the y-axis, and the x-axis is the speed. And each curve is at a different temperature. Here you have 0 Celsius, and that's equal to 273 Kelvin. Didn't even tell you that conversion yet, but there it is. And look here, here's 1000 Celsius, 1273 Kelvin. Can you see a pattern? Here's 2000 Celsius, 2273 Kelvin. Also note that there's no degree sign in front of the Kelvin. So let's look at the table now, and let's erase all this so we can see it. Here we go. Let's interpret this. We have our lowest temperature here. It has a lot of particles moving at this speed. I come over to the 2000 Celsius, the blue one, and look at this. This has a lot of particles moving at a higher speed, and the red curve at 0 Celsius doesn't have as many. And then when you go out to this area, 0 Celsius has nobody moving at that speed, but your 2000 Celsius and 1000 Celsius do. Well, actually just the 2000. The 1000 cuts off there also. So when you average all of these, you will get a much higher average temperature. So you have a greater average kinetic energy. Here's the 3 scales. And with any luck, you've already seen these somewhere in your travels. And the conversion there is, let's see, to go to degrees Fahrenheit, you take 9/5 C and you add 32. a degree there. Celsius you get 5/9 degrees Fahrenheit minus 32. And then Kelvin, hopefully you figured that out from the previous slide, is just 0 degrees centigrade plus 273. And what do we have? Some key points here. The boiling point of water in Fahrenheit is 212, kind of an arbitrary number. Celsius is much cleaner. It's 100. Water freezes. Celsius again is just at 0. And let me erase over here. Fahrenheit's at 32, an uncomfortable number again. And then what we have with Kelvin, basically the key advantage there, absolute 0 is actually 0. Where for Celsius, absolute 0 is minus 273. So right here, this is what's used in the System International units. For the rest of this unit and beyond, we're just not going to work with Fahrenheit, okay? That's used in your everyday life, not going to be used in science. And Kelvin typically is more often used, but Celsius is appropriate also. And here's your conversion factors. And once again, note that there's no degree in front of Kelvin. And here's a quick sample solution here.